Fine. Let's start. In December 2004, a star 50,000 light-years away changed Earth's atmosphere. One star, one burst, from the other side of the galaxy, and we had no idea it was coming. That's the thing about neutron stars. They operate at scales and speeds that feel almost deliberately hostile to human comprehension. They are city-sized objects with the mass of the sun, spinning thousands of times per second, wrapped in magnetic fields so intense that the space around them behaves differently than space anywhere else. And every few years, one of them does something that makes physicists stare at the data and quietly say, that shouldn't be possible. 10 of them. 10 things that shouldn't be possible. Let's go. Number 10. In 2003, astronomers detected something extraordinary. A magnetar, which is an especially violent type of neutron star emitting radio waves. That was already unusual. Most magnetars don't do radio. This one did, and we gave it the name XTE J1820-197, and we watched it carefully. Then, in late 2008, it stopped. Not slowed down. Not faded gradually. Stopped. One day, it was broadcasting. Then, it wasn't. For 10 years, nothing. No signal. No signal at all from an object that had been the first of its kind ever detected in radio. Now, a magnetar going quiet isn't completely unheard of. They're volatile. They flare. They settle. Fine. But 10 years is a long time to hold your breath, and by 2018, most astronomers had mentally filed this one under probably done. Then, on the 8th of December, 2018, the Lovell telescope at Jodrell Bank Observatory picked up a bright pulsed radio signal. XTE J18T-197 was back. Here's the thing, though. When they looked closely at the signal, it wasn't quite the same signal as before. The pulse profile had changed. The geometry of the emitting region, the specific shape and timing of how radio energy was pouring out of the star, had physically shifted during the silence. Something changed inside that star during the decade it spent being quiet. We can't tell you what, because we don't know. We couldn't see inside it. We could only read the letter it sent after it decided to start writing again and noticed that the handwriting had changed. A star, 50,000 light-years from Earth. Silent for a decade. Then, without warning, different. Number 9. There is a pulsar in the globular cluster Terzan 5, about 28,000 light-years away, named PSR J1748-2446 AD. It holds a record. It spins 716 times per second. 716. A kitchen blender tops out at around 500 rotations per second, and we think of that as impressively fast. This neutron star is faster, and a kitchen blender isn't a star. The equatorial surface of PSR J1748-2446 AD, the material right along its widest point, is moving at roughly 24% of the speed of light. 1/4 of the speed of light just as a surface condition. As in, that's just what it's doing, all the time. Now, at that spin rate, the star has to be almost impossibly small to hold itself together. If it were any wider than about 16 kilometers across, the centrifugal force at the equator would exceed the gravitational pull, and material would simply leave. Flung into orbit, just gone. The only thing keeping this star in one piece is the fact that gravity at its surface is roughly 200 billion times stronger than Earth's. Which raises the obvious question, how did it get this fast? The answer is that it has a companion star, and over billions of years it stole mass from that companion, and each stolen parcel of mass carried angular momentum with it, and the pulsar used all of that to spin up, incrementally, across geological timescales, until it hit 716 rotations per second, and apparently decided that was enough. The companion star, for its trouble, now orbits the pulsar every 26 hours. It also eclipses it for about 40% of every orbit, which means this record-holding, light-speed-adjacent gravity monster of a pulsar gets briefly blocked from our view every single day by the star it robbed. It seems a bit ungrateful. Number 8. The categories we use to sort neutron stars feel solid. There are pulsars, rotation-powered, spinning fast, emitting radio beams as they go. And there are magnetars, powered by the decay of enormous magnetic fields, occasionally violent, the source of some of the most energetic bursts in the known universe. Different objects, different physics, different boxes. PSR J11196127 would like a word. In late July of 2016, a previously ordinary radio pulsar emitted 2 intense hard X-ray bursts. These weren't radio pulses. These were the kind of high-energy eruptions that magnetars produce. Fermi detected them. Swift detected them. 12 bursts in total across the active period. The X-ray flux jumped by a factor of at least 160. And then the radio signal disappeared. The star, which had been quietly doing its pulsar thing, went X-ray active in a way indistinguishable from a magnetar outburst, and simultaneously stopped broadcasting in radio. For weeks. Then the radio came back. The X-ray settled down, and PSR J11196127 went back to being a pulsar. The reason this matters is that the magnetic field of this star, about 4 times 10 to the 13th Gauss, sits right in the borderland between pulsar territory and magnetar territory. It apparently needed only a brief internal rearrangement to tip over the line, to stop being one thing and start being another, and then tip back. We tend to think of the categories we've invented for objects in the universe as reflecting real distinctions, and they often do. But every so often, the universe sends something across a boundary we thought was fixed, just to remind us that the map is not the territory. The border between a pulsar and a magnetar. Turns out it's more of a suggestion. Number 7. In 2019, NASA's NICER telescope, which is mounted on the International Space Station and designed to observe X-rays from neutron stars, published results from a detailed mapping of pulsar PSR J3+0451, and what it found broke something that had seemed unbreakable for 50 years. The standard picture of a pulsar's magnetic geometry is a centered dipole. 2 poles, north and south, on opposite sides of the star, like a bar magnet. Hot spots at each pole, antipodal, symmetrical. It's the picture in every textbook. It's the picture that's been there since pulsars were discovered in 1967. Both hotspots on PSR J03+0451 are in the same hemisphere, not opposite sides, the same side. One of them is crescent-shaped. Both are pointing away from us, toward the hemisphere facing the other direction. No centered dipole magnetic field can produce this. To get this geometry, you need something more complex. Higher-order magnetic field configurations, offset from the center, multipolar in structure. Here's what makes this unambiguous. 2 completely separate teams analyzed the same NICER data independently, using different statistical models, different analysis frameworks, different code, and they both got the same answer. The same impossible geometry. It wasn't a glitch in the analysis. It was the star. 50 years of pulsar diagrams. The 2-beam lighthouse. The 2 antipodal poles. That picture is not wrong exactly. It applies to many pulsars, maybe most of them. But for this one, the textbook was quietly, firmly incorrect, and NICER found the edge of the map. There are probably others. We're just now getting the tools sensitive enough to find them. Number 6. The term Black Widow pulsar is astronomers being unusually poetic and unusually accurate. A Black Widow pulsar is a neutron star in a binary system that is actively destroying its companion. Not passionately, not dramatically. Methodically, over billions of years, irradiating the companion star with intense radiation, boiling off its outer layers, reducing it progressively from a full star to a planetary remnant. PSR J0952-0607 is the most successful Black Widow we know of. When Roger Ramani and his team at Stanford published their results in July of 2022 using the Keck telescope in Hawaii, they measured the pulsar's mass at 2.35 solar masses, plus or minus 0.17. That is the highest well-measured mass for a neutron star ever recorded, and it got there by eating. The companion, once a full star, is now roughly 20 times the mass of Jupiter, a large gaseous planet, essentially, still being heated, still being evaporated. It orbits the pulsar every 6.42 hours, close enough to be blasted by radiation from a star that spins 707 times per second. That spin rate matters. Neutron stars are born spinning fast, but they slow down over time. The only way to spin this fast at this age is mass transfer, stolen angular momentum from a consumed companion. Every bit of mass it took, it also took speed. The more it ate, the faster it went. Here's the strange part. The accretion of that mass also buried the pulsar's magnetic field. The more it consumed, the magnetically quieter it became. Its current surface magnetic field is about 60 million Gauss. For a neutron star, that is almost nothing. The most massive known neutron star is also among the most magnetically inert, and it sits right at the edge, above approximately 2 to 2.2 solar masses. Current models suggest a neutron star should collapse into a black hole. PSR J0952-0607 is at 2.35. It has been consuming mass for billions of years and is still, just barely, a neutron star. The companion has about a Jupiter's worth of mass left, give or take. At some point, one assumes the math catches up. Number 5. There is a line in pulsar physics called the death line. It's not metaphorical. Well, it is, but it maps onto real physics. As a pulsar ages and slows down, the processes that generate its radio emission become less and less efficient. Below a certain spin rate, above a certain age, the electromagnetic machinery simply stops working and the pulsar goes quiet. Dead. Silent. PSR J0901-4046 rotates once every 75.885 seconds, and it is still broadcasting in radio. To put that in context, before this discovery in 2022, the slowest known radio-emitting neutron star had a period of about 23 seconds. PSR J0901-446 is more than 3 times slower than that. By every model we have, it should have crossed the death line millions of years ago. It should be invisible. It isn't. Dr. Manisha Caleb's team at the University of Sydney found it using the Meerkat radio telescope in South Africa, and initially, they almost didn't notice it. The source was identified from a single pulse. One lone radio blip caught while the telescope was observing something else. One accidental signal from a star that shouldn't be talking. When they followed up, it got stranger. PSR J0901-4046 emits in at least 7 distinct pulse types. 7 different modes of emission. Some look like pulsar pulses. Some look like magnetar bursts. Some resemble fast radio bursts. Those bright, millisecond duration flashes usually seen in distant galaxies. It has the highest magnetic field strength ever measured in a radio pulsar. A later study classified it as the most magnetized radio pulsar known. It does not fit in any box we currently have. A follow-up study pointed out that detecting sources like this is observationally very difficult because radio telescopes typically don't search for pulses this slow, or pulses that last more than a few tens of milliseconds. Which raises the obvious question: how many others are out there, broadcasting from beyond the death line, into a sky nobody is looking at? Number 4. Since the first pulsar glitch was recorded in 1969, astronomers have cataloged hundreds of them. A glitch is when a neutron star suddenly spins up, just slightly, just briefly, typically attributed to angular momentum transfer between the star's superfluid interior and its solid crust. They're not fully understood, but they follow a clear rule. They are always spin-ups. Every glitch ever recorded had involved a neutron star rotating faster than it had a moment before. Until April of 2012. The Magnetar 1E 2259 Pli 586 was being monitored by the Swift X-ray telescope as part of a regular timing campaign, and on approximately the 18th of April, something happened. The pulsar's rotation frequency dropped. Abruptly, a sudden, clear, unambiguous spin down. An anti-glitch. The lead author, Robert Archibald at McGill University, described it precisely. What is really remarkable about this event is the combination of the magnetar's abrupt slowdown, the X-ray outburst, and the fact we now observe the star spinning down at a faster rate than before. A week before the timing anomaly, on April 21st, a 36 millisecond X-ray burst had been detected from the magnetar's direction by Fermi. The burst may have been a signal of whatever internal rearrangement caused the spin down. Or maybe the burst caused it. The causal chain isn't settled. One published explanation, which reached peer review and was taken seriously, is that a solid body, an asteroid-like object, struck the magnetar carrying retrograde angular momentum. Angular momentum pointing the wrong way, and the star recoiled. A neutron star hit by a rock, visibly flinching in the timing data. That might not be the right answer. Magnetospheric torques and internal superfluid dynamics are the more mainstream candidates. But here's the thing. Nobody has proven the anti-glitch mechanism definitively. And then, in April of 2019, it happened again. A second anti-glitch. This time with no X-ray burst. No external signal at all. It just quietly spun down, in isolation, without announcing itself. The same star. The same impossible behavior. Silent this time. Internal. Invisible except in the timing. The rule held for 5 decades and hundreds of observations. Then it broke twice. Number 3. In 1974, a 24-year-old graduate student at the University of Massachusetts named Russell Hulse was conducting a systematic pulsar survey using the Arecibo Observatory in Puerto Rico. He'd been finding new pulsars, cataloging them, moving on. Routine work, mostly. Then he found one where the period varied. A pulsar's period isn't supposed to vary. That's rather the point of a pulsar. They are, famously, some of the most precise natural clocks in the universe. A varying period suggested noise, equipment artifact, something wrong with the data. Hulse nearly discarded it. His supervisor, Joseph Taylor, talked him out of discarding it. What they had found was the first binary pulsar, a neutron star in orbit with another neutron star. The period wasn't varying randomly. It was varying in a regular, predictable pattern because the pulsar was Doppler shifting its own pulses as it moved toward and then away from Earth in its orbit. The variation was the orbit. They named it PSR B1913 Pulsar and started timing it carefully, very carefully. Here's what general relativity predicts. 2 massive objects orbiting each other should lose energy by radiating gravitational waves. As they lose energy, the orbit should shrink. The orbital period should decrease. Slowly, but measurably. Einstein's equations give you a very specific number for how fast. After 8 years of observation, Taylor and his team reported the orbit was decaying at exactly the rate Einstein predicted, to within a fraction of a percent. They had just proven that gravitational waves exist. Not directly, they hadn't detected the waves themselves, but they had detected the energy loss, and there was only one thing in physics that could carry energy away from that system. The Nobel Prize in Physics for 1993 was awarded to Hulse and Taylor for the discovery. The direct detection of gravitational waves by LIGO happened in 2015, 41 years later. 41 years between indirect proof and the ability to actually hear them. Hulse almost didn't keep the data. The data almost became noise on the floor of an observatory in Puerto Rico. Instead, it became the first handshake between neutron star physics and gravitational wave astronomy. Because a graduate student found an anomaly in his timing measurements, and, for once, someone said, "Wait." The universe had been broadcasting that answer for decades before we had the instrument to hear it clearly. Hulse's pulsar found the signal first. Number 2. December 27th, 2004, 21:30 UTC. A burst of gamma radiation struck Earth's upper atmosphere. Multiple spacecraft were hit simultaneously. Some had their detectors completely saturated, meaning the instruments simply couldn't measure how bright it was. They'd gone off the scale. Some automatically switched into protective modes. There were instruments aboard satellites that were not pointed anywhere near the source and still recorded the event, because the signal was powerful enough to reflect off the moon and hit them from the other direction. The source was the Magnetar SGR 180620, located approximately 50,000 light-years away in the constellation Sagittarius. In 1/5 of a second, it released roughly 2 times 10 to the 46th ergs of energy. To make that feel real, that is more energy than the sun will emit across the next 250,000 years. Released in 1/5 of a second. By one star. That we didn't know was about to do this. The burst was so energetic that it ionized Earth's upper atmosphere, the ionosphere. It measurably changed the electromagnetic properties of our planet, from 50,000 light-years. After the initial burst, a radio afterglow was detected expanding outward from the magnetar at roughly 25% of the speed of light. The outflow contained at least 4 times 10 to the 43rd ergs in the form of magnetic fields and relativistic particles, creating a briefly resolved radio nebula that astronomers tracked over the following weeks. Now here's the part where the scale stops being impressive and starts being something else. If SGR 180620 had been within about 10 light-years of Earth, roughly the distance to our nearest stellar neighbor, the gamma radiation from that burst would have significantly depleted Earth's ozone layer. Depending on geometry and intensity modeling, some calculations suggest effects comparable to a mass extinction event. It was 50,000 light-years away, and it changed our atmosphere. There was no warning. SGR 1806-20 had been cataloged and monitored. Astronomers knew it was a magnetar. They knew magnetars occasionally flare. Nobody predicted this event. Nobody could have. We found out when the instruments registered it. When the sky, on an otherwise unremarkable December evening, briefly said something. Number 1. This one is quieter than the rest. No flare, no blast, no asteroid strike, no alarm on a spacecraft. Just a cooling curve. A small, consistent drop in surface temperature recorded across a decade of observations. 2% per decade. A number that would mean nothing by itself except that it was too fast. The star was cooling faster than it should have been, and 2 separate groups of physicists on different continents, independently looking at the same Chandra X-ray data, arrived at the same explanation within weeks of each other without knowing the other was working on it. The neutron star in the Cassiopeia. A supernova remnant, sitting about 11,000 light-years away, is approximately 330 years old. Young for a neutron star. It was first discovered in 1999 as part of Chandra's very first observations. Its surface temperature sits around 2 million Kelvin, and between 2000 and 2010, it cooled by roughly 2%. 2% doesn't sound like much. 2% of 2 million degrees is 40,000 degrees of temperature loss in a decade, and the reason matters more than the number. What Danny Page, Madhapa Prakash, James Latimer, and Andrew Steiner proposed in their February 2011 Physical Review Letters paper, and what Peter Sternen and colleagues in St. Petersburg proposed independently at almost the same moment, is that the cooling is caused by neutrinos. specifically by the onset of neutron superfluidity in the star's core. Superfluidity. Inside a star. You've probably heard of superfluids. Liquid helium cooled below about 2 Kelvin becomes 1, flowing without friction, climbing walls, defying intuitive behavior. The superfluidity in this neutron star's core involves neutrons. Actual neutrons, the particles that make up the interior of every atom, pairing up into what physicists call Cooper pairs, like electron pairs in a superconductor. And when that pairing happens, when the neutrons undergo that phase transition, they emit a burst of neutrinos. Energy is radiated away. The star cools faster. The core of Cassiopeia A's neutron star is sitting at roughly 5 times 10 to the 8th Kelvin, which sounds enormous until you realize that this is cold enough for neutron superfluidity to occur. The protons in the core had already gone superconducting at higher temperatures years earlier, before we were watching closely enough to see it. The neutrons are only now crossing their threshold. We watched it happen. Not a simulation. Not a prediction. An observation. A quantum phase transition. Matter-changing state at the subatomic level. Occurring inside an object 11,000 light-years away. Detectable only as a tiny drop in surface temperature, measured across a span of years by a telescope in space. 2 groups working in parallel, neither aware of the other, both arriving at the same answer. The physicists at Chandra headquarters, when both papers landed close together, later described it as a genuine race with a simultaneous finish. And here's the thing that is worth sitting with. We didn't watch this star explode. We didn't catch it in a burst, or a flare, or a collision. There was no event. There was just a measurement, repeated consistently, over a decade, that came back slightly colder than the last time. And in that cooling curve, in that patient, unremarkable line of data points trending downward, was a record of something happening deep inside a collapsed stellar core that no instrument can directly observe. The most exotic form of matter in the known universe, changing its fundamental state, and the only evidence was a 2% temperature drop on a surface 2 million degrees hot. The universe doesn't always make noise when it does something extraordinary. Sometimes it just gets a little colder, and if you're paying attention, you can find out what it's doing in the dark. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next